this is our AP Chemistry Chapter 2 lesson video part 1, and we're going to cover section 2.1 through 2.4. So, important thing to note, if you're in my class, you should already know all of this from honors chemistry. Okay, so my PowerPoint is not going to be super long and informative. We're just going to do a lot of practice. Okay, I will slow down and do longer lesson videos on the content you haven't learned yet. Alright, so section 2.1, the atomic theory of matter. Democritus was the first to describe atoms as indivisible, and then as we talked about before, Dalton's atomic theory states that each element is composed of extremely small particles called atoms. All atoms of a given element are identical, but the atoms of one element are different from atoms of another element. Atoms of one element cannot be changed into atoms of a different element by chemical reactions. Atoms are neither created nor destroyed in chemical reactions or physical processes. Compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kinds of atoms. So again, this is just some of the basic information they were determining about atoms when we were trying to figure out, what are atoms? Are they something? What's matter made of? And then how do they work and what are they made of? And so that's what this chapter is starting with. It's just the discovery of the parts of the atoms. So some laws that apply for atoms. The law of constant composition states that in a given compound, the relative number and kinds of atoms are constant. The law of conservation of mass states that the total mass of the materials present after a chemical reaction is the same as the total mass present before the reaction, so mass can neither be created nor destroyed. The law of multiple proportions states that if two elements, A and B, combine to form more than one compound, the masses of B that can combine with a given mass of A are in the ratio of small whole numbers. So that's why a lot of formulas are like H2O or H2O2. They form that low, small whole number ratio. So, discovery of the atom. So once we determined that matter's made of atoms, how did we get to the whole protons, neutrons, and electrons thing? Well, J.J. Thompson discovered electrons using the cathode ray tube. My video wouldn't play, it says it's blocked, but there's many that you can find. But what happens is the cathode ray is this glowing green beam. It normally goes straight across from the cathode and anode. But if you look, it's bending down. That's because he's holding a magnet near it. So what he found was the cathode ray would bend away from a negative source. So if it's going to bend away from a negative, be repelled by a negative, it must be made of negative particles. And so he called those electrons. Ernest Rutherford or Eugene Goldstein are given credit for discovering protons, and then James Chadwick discovered neutrons. So J.J. Thompson, once he did his cathode ray experiment and determined that electrons existed, he made what we call the Plum pudding model of the atom. And it looks like this. It's a large positive area with electrons throughout. Rutherford decided to test the Plum pudding model by shooting alpha particles, which are just double positive particles, at gold foil. So this is kind of the setup of his experiment. Since some of the alpha particles bounced back and did not pass through the foil, Rutherford determined that there was a dense positive nucleus at the center. So see, if Plum pudding model was accurate, all of the particles should have passed through, and they would have had slight deflection due to the fact that it's passing through a positive area. But some actually hit and bounced back, so that means they didn't pass through like a positive area, they hit something dense and positive. So he discovered the nucleus. However, many of the alpha particles passed straight through and didn't hit anything. They didn't deflect, bounce back, they just passed straight through. So Rutherford determined that most of the atom is empty space. So in other words, most of the atom is the electron cloud, which, yes, has some electrons in it, but the majority of it is empty space. So, section 2.3, the modern view of the atomic structure. The charge on an electron, like the actual calculated charge, is negative 1.602 times 10 to the negative 19 coulombs. As you can imagine, that is very time consuming to write over and over again, so we say it has a negative 1 charge. And then the charge on a proton is the same value, but opposite sign, positive 1.602 times 10 to the negative 19 coulombs, but for simplicity we say it's a positive 1 charge. Neutrons, of course, have no charge, and then because atoms themselves are neutral, they have the same number of protons as they do electrons. Oh gosh, that should say electrons. My goodness, I need to go in there and change that. So since atoms are so small, a unit called angstroms is commonly used for an atom's diameter. 1 angstrom is 10 to the negative 10 meters. And the abbreviation for angstrom is a capital A, and then it has like a little almost degree sign, but right above the A. As you can imagine, it's awkward to try to type that in, so you'll see me just write angstroms when I'm typing. But if I actually write it out in a problem like you'll see in a few minutes, you'll see me write the capital A with the little circle above it. So the atomic mass unit, or AMU, is used for the masses of atoms, and 1 AMU is 1.66054 times 10 to the negative 24 grams. So in other words, y'all, we're talking about 10 to the negative 24 grams. A gram is already only about the size of a paperclip, and we're talking about 10 to the negative 24. So we're talking about a decimal, 23 zeros, and then we start having numbers. So that's why we have AMU, because atoms, of course, are so tiny. So most of the space of an atom is the electron cloud, but most of the mass of the atom is in the nucleus, the protons and neutrons. So the protons and neutrons have all the mass, but the electron cloud takes up all the space. So since electrons have almost 2,000 times less mass than protons and neutrons, so an electron is about 1,836 times less mass than a proton or neutron, so their mass just isn't important when we're adding up atomic mass. So atoms are identified by the number of protons, because we'll talk about isotopes, so neutrons can change. We'll talk about ions, electrons can change. Protons cannot change through chemical or physical processes. So an atom can always be identified by its number of protons. The number of protons is the atomic number. It can be found at the top of the box on the periodic table. However, when we're writing in shorthand, like when you see something like this, atomic number is the bottom number. Okay, so on the periodic table, it's the top number. When we write in shorthand, it's the bottom number. Since atoms have no charge, they have the same number of protons and electrons. All right, so I wrote that there. I don't know what happened here. I don't know what happened there. I need to change that to electrons. All right, so yay, first question. So let me flip so that way you don't have to sit here and waste time watching me use a calculator. All right, so it says the diameter of a US dime is 17.9 millimeters, and the diameter of a silver atom is 2.88 angstrom. How many silver atoms could be arranged side by side across the diameter of a dime? Okay, so the problem is we know the diameter of a dime, we know the diameter of a silver atom, but they're two different units. We have millimeters and we have angstroms. So we just need to get the units equal. So y'all keep in mind, whenever I show you a math problem, there's more than one right way you can do it. So I can change millimeters to angstroms, or I could change angstroms to millimeters. I chose to change angstroms to millimeters, but it doesn't matter what you do. All right, so I start with 2.88 angstrom, and like I said, the symbol for angstroms is just A with the little circle above it. And so I know from the other slide a minute ago that 1 angstrom is 10 to the negative 10 meters. So that's great, but I'm trying to get to millimeters, so I got to do one more step. So 1 millimeter is 10 to the negative 3 meters. So then my meters cancel. So once I do that, I can multiply and divide and get 2.88 times 10 to the negative 7 millimeters. Okay, so that means this is the diameter of 1 silver atom. So we're trying to figure out how many silver atoms could go across a dime of 17.9 millimeters. So all we need to do at that point is divide. So I do 17.9 millimeters, and I divide by my 2.88 times 10 to the negative 7 millimeters. My millimeters cancel, and so I ended up getting 6.22 times 10 to the 7 atoms of silver. Okay, and so that's all you have to do in this case, is we know that we can just divide the two numbers to figure out how many silver atoms, but we just got to get the units the same. Okay, it's always important that your units cancel whenever you're doing a math problem. All right, so hopefully that wasn't too bad. Just more converting, like from chapter 1. Alright, so it says, which of the following factors determines the size of an atom? Well, y'all, before I even look at the answer choices, I know the mass of the atoms in the nucleus, the size of the atom is based on the electron cloud. So the volume of the nucleus, no, the nucleus is going to be super tiny. The volume of space occupied by electrons in the atoms, there we go. Because that's the volume of the electron cloud, which is what I'm looking for. Alright, so that one should have been super easy. Hopefully no explanation needed. Alright, so maybe pause it and try these two on your own so you can get some practice converting and using angstroms. But it says the diameter of a carbon atom is 1.54 angstroms. Express this diameter in picometers. So I just start with my angstroms, 1.54, and I know that 1 angstrom is 10 to the negative 10 meters. So my angstroms cancel. Then I know 1 picometer is 10 to the negative 12 meters. So my meters cancel. So then all I do is just multiply and divide. So when I did that, I got 154 picometers. Just like that. That's all I had to do. Super easy. You may have had to look up pico on your SI prefixes chart because we don't use that one very often. Alright, then it says how many carbon atoms could be aligned side by side across the width of a pencil line that's 0.2 millimeters wide. Well, yeah, now we have 3 units we could use. We know we got millimeters. I could change picometers to millimeters. I could change angstroms to millimeters. I could change millimeters to picometers or millimeters to angstroms and divide. Like, it literally doesn't matter. So what I chose to do was I chose to change my millimeters. So I started with 0.2 millimeters. And so I know that 1 millimeter is 10 to the negative 3 meters. All right. And then I went to picometers. So I said 1 picometer is 10 to the negative 12 meters. And then I said that 1 carbon atom is 154 picometers. Okay, because I'm just trying to show you how there's more than one way. Like in the first one, I stopped, got my answer, and then divided. In this one, I just used it as a conversion factor. It doesn't matter. You're going to get the same answer. All right, so I multiply and divide, and for this one, I got 1.3 times 10 to the 6 atoms of carbon. So just remember, y'all, as long as the other way you do math works for everything, then you're more than welcome to do it. Okay, math questions almost always have more than one possible way that you can work it out. Now, the problem arises if you only get it right sometimes. That means your method is not great. Alright, so atomic number is number of protons. The mass number of an atom is the number of protons and neutrons in the nucleus of the atom. To calculate the number of neutrons, you can do mass number minus atomic number. Isotopes are atoms of the same element that have different numbers of neutrons. They have the same atomic number since they have the same number of protons. They have to have the same protons to be the same element, but different mass numbers since the neutrons are not the same. So it says how many protons, neutrons, and electrons are in an atom of gold with 197. So y'all, the top number in shorthand is the mass number. Okay, the bottom number, which they have chosen to leave off, which is fine, is atomic number. So to get protons, I would look at the periodic table. So y'all, for this chapter, you're definitely going to want a periodic table. I have one right over here. So I can see that the atomic number is 79. So there's 79 protons. Since it says they're atoms, I also know that means there's 79 electrons. So how do I get neutrons? Well, I just do mass minus atomic. So I can just do 197 minus 79, and that gives me 118. So I have 118 neutrons. Alright, so that's one form of shorthand where you have a superscript of mass number and usually a subscript of atomic number. The atomic number could be left off because it can't change. The other form of shorthand is the name dash the mass. So again, this is the mass number. So where would we find atomic number? The periodic table. So strontium, now look at the periodic table, it's SR, it's number 38. So it has 38 protons. Because it's an atom and it's neutral, it has 38 electrons. So then to get neutrons, I just do 90 minus 38 and I get 52 neutrons, just like that. Okay, y'all, this should be super easy. Like if you were even lucky enough to get a question like this on the AP exam, count your blessings, because this is super easy. So again, if you're struggling now, that's rough. All right, so the next one says, which of these atoms has the largest number of neutrons? So I actually had two that both had the largest amount when I did this one, so I'm not sure if it was supposed to have two as the answer or not. I pulled these from the textbook though. Okay, so all I did was I sat there and found the atomic number of each element on the periodic table, and I did mass number minus atomic. So I'm just going to put how many neutrons I got for each one. So for this one, I got 85 neutrons. For this one, I got 91. For this one, I got 89. For this one, I got 95. And for this one, I got 95. So see, that was the problem I had, was I had two with the highest amount. Okay, and see how, again, all I did was do mass. So I'll just show you how I got 85. I'm not going to do all 5 of them. So for europium, I did 148, which is the mass, minus, and then I just found it on the periodic table, and it is 63. And got 85. Just like that. That's all I did, and I did that for each element. So I got 2 answers for this one, like I said, D and E. Well, I guess I could have just clicked my way through this whole thing instead of writing it out. Would have saved some time. All right. So next, and again, make sure you're pausing these and trying these on your own. It doesn't matter if I know how to do them. So it says how many protons, neutrons, and electrons are in these atoms. So for barium, I'll look up the atomic number. It's 56. So I have 56 protons because it's an atom. I have 56 electrons. And then get neutrons, I do 138 minus 56. And I got 82 neutrons. So again, y'all remember the superscript is the mass, or if it's written like that, that's the mass. If it was going to give me atomic number, also in the shorthand, it would be written as a subscript. All right, so phosphorus. So I look at phosphorus on the periodic table, P, it tells me 15 protons. Because it's an atom, it has to have 15 electrons. Then I just did 31 minus 15 to get 16 neutrons. All right, so again, hopefully questions like these are super easy. Hopefully I'm jogging your memory of some things you learned in honors chem but might have forgotten. All right, so it says magnesium has 3 isotopes with mass numbers 24, 25, and 26. Write the complete chemical symbol, superscript and subscript, for each. Okay, so I know the symbol for magnesium is Mg. I know the atomic number for magnesium is 12 every time. So one of them has a mass of 24. So it would look like this. One of them has a mass of 25. So it would look like this. And one of them has a mass of 26. So it would look like this. So see, they're all magnesium because they all have atomic numbers of 12. But their masses are just changing. Then it says how many neutrons are in an atom of each isotope. Well, it's super easy when you have those numbers, you just subtract down. So 24 minus 12 is 12 neutrons. 25 minus 12 is 13 neutrons. 26 minus 12 is 14 neutrons. Super easy. Or hopefully it is. Again, y'all, if you're struggling now, whew, it's going to be rough when we get to equilibrium. All right. So it says, which of the following is an incorrect representation for a neutral atom? Well, if I look, lithium is 3 on the periodic table, so that's good. Carbon is 6 on the periodic table, so that's fine. Copper is 29 on the periodic table, so this one would be the one that is incorrect. It shouldn't have a 30 down there, it should have a 29. Alright, and so again, y'all, something like this should be super easy for you to pick out the wrong one. Okay, make sure you're trying these too. Alright, so it says give the complete chemical symbol for the atom that contains 82 protons, 82 electrons, and 126 neutrons. Well, first I got to figure out what element it is. So it tells me 82 protons, so I'll look at the periodic table. Number 82 is lead, so it's Pb. That's a 2. Don't know what was happening there. Alright, so since it has 82 protons, I'll put my 82 down here. It has 126 neutrons. Now, you don't put neutrons right here, you put mass. Mass is protons plus neutrons. So I need to do 126 plus the 82, and that gives me 208. And so there's my complete symbol, superscript and subscript. Okay, so make sure you don't accidentally just put neutrons on top. That happens sometimes. You got to do the whole mass, which is the whole nucleus, protons and neutrons. All right, so last section in this video, atomic weights. So the mass number is the number of protons and neutrons in an atom. So it's going to be a whole number every time. The atomic mass that you see on the periodic table, though, is an average mass of all the isotopes of the element multiplied by their relative abundance. So it's kind of like your grades, how all your grades don't count the same percentage. All the isotopes don't have the same percentage. So you just do the mass times its percent, the mass times its percent, so forth and so on, and then you can add them up to get the total. We did this in honors. All right, so our first question, it says naturally occurring chlorine is 75.78%, chlorine 35, which has this mass, and 24.22% chlorine 37, which has this mass. Calculate the atomic weight. So y'all, this is where, remember, we take our decimal out of decimal form. The way you do that is turn it into a decimal, we take it out of percentage form. Turn it into a decimal. You either divide by 100 or move your decimal 2 places to the left. Then all we do is we take the mass. So see, there's one of my masses, 34.969 AMU, and multiply it by its percent, but in decimal form, 0.7578. And then we just add the other one. So it has a mass of 36.966 AMU, and we multiply that by 0.2422. So all we have to do is make sure to change our percentages to decimal form. So once I do all that, I get about 35.45, and then of course my unit is AMU. Okay, super easy. We did this in honors. It should be super easy. Again, if it's not, oh man, it's gonna be rough. It is gonna be rough. All right. So moving on, it says there are 2 stable isotopes of copper found in nature, copper 63 and copper 65. If the atomic weight of copper is 63.546 AMU, which of the following statements are true? Well, A says copper 65 contains 2 more protons than copper 63. Well, isotopes don't have different numbers of protons, they have different numbers of neutrons. Otherwise, they can't both be copper, so it's not that one. Copper 63 must be more abundant than copper 65. Well, if you look, 63.546 is closer to 63 than it is to 65. The closer the atomic mass is to one of the isotopes, the more abundant that isotope is. All right, that's what that means. Oh, and then of course, C says all copper atoms have a mass of this. Remember, that's the average. So each copper atom does not have that mass. That's just the average masses once you combine all the isotopes by their percentage. All right, so make sure you're practicing these on your own. Don't just watch me do them. All right, so let's look at this one. So it says 3 isotopes of silicon occur in nature. You have 28 with about 92%. You have 29 with about 5%, and you have 30 with about 3%. Calculate the atomic weight. So yeah, we're just going to do the same thing. We grab the mass. So my first mass that they gave me is 27.97693 AMU. Now we're going to multiply it by its percentage, but as a decimal. So I'm going to move it over twice. So times 0.9223. All right, then I do my next one. So my next mass, let's see, is 28.97649 AMU. I'm going to multiply that as by its percentage of the decimal, but remember you move the decimal twice or divide by 100. A lot of you just want to put the decimal in the front, but you have to move it over 2 spots. So I'm going to multiply by 0.0468. And then we just do it for our last one. Our mass is 29.97377 AMU times my percentage as a decimal. So again, I'm going to move it twice. So I'm going to multiply it by 0.0309. And once I do all that, I end up getting about 28.09, don't forget your units, AMU. All right. So again, just like with chapter 1, this is just review. Hopefully it's all coming back to you, but this is stuff you should already know from honors chem. All right?